Hello, dear students. So hope you all will be fine. Uh, this is the first lecture of this course, Real Analysis Second, MMTC 202. The recommended book for this course is Principles of Real Analysis, written by Alpritz and Birkinshaw. We start this course, or we start this lecture with the definition of Semirings, and then we check certain properties of Semirings. To begin this lecture, we give an example of Semiring. Example of a Semiring on a real line. So let A and B, let A and B be any two real numbers. Define the semi-closed interval A, B. It's equal to this set of all real numbers such that A less or equal to X less than B if A is less than B. Like 1 and 2. If I set A equal to 1, B equal to 2, then this semi-closed interval 1, 2 is equal to set of all real numbers X such that 1 less or equal to X less than 2. And this semi-closed interval AB is equal to phi if A is greater or equal to B. So this is phi in case A is greater or equal to B. For example, the semi-closed interval 1 and 1, because there is no any real number which lies between 1 and 1. So we take this semi-closed interval to be equal to be phi in case A is greater or equal to B. Now let's consider the following class of sets. Let S be the class of let S be the class of all such semi-closed intervals. Be the class of all such semi-closed intervals. We show that this class has following properties. First property is this class should contain phi. Phi is a member of this class. And second property is if we choose any two members from this class, say A1, B1, and semi-closed interval A2, B2 belongs to phi, then their intersection should be in phi. A1, B1 intersection A2, B2 should be in S. First property, phi should be the member of S. Second property, this if we choose any two members from the class S, then their intersection should be the member of S. That means S is closed with respect to finite intersection. And third property, which is very important, if A1, B1, comma A2, B2 be any two members of S, then the set difference A1, B1 minus A2, B2 must be equal to the finite disjoint union of members of S. That means it's equal to C1 union C2, so on up to Cn, where these CIs, they are the members of S and they are also pairwise disjoint for all I not equal to j, and 1 lesser equal to I comma j lesser equal to n. That's the third property. Third property is if we choose any two members of S, then their set difference must be equal to the finite disjoint union of members of S. We show that this class S has these three properties. So first property is trivial. First, let's check first property. Since phi is equal to, because there does not exist any real number between a and a, so it's phi and it's a member of, or by definition it's equal to phi and it's a member of S. So S contains phi. Now we check second property. Second property, that's if I choose any two members of S, then their intersection must be the member of S. Let A1, B1, comma A2, B2 be the members of S. The members of S. We show that A1 intersection A2 is also the member of S. That means this intersection is also a semi-closed interval. It is. So let's take the following cases to prove its intersection is a member of S. So we take following cases. Case number 1. First case. So first case is in case these two members of S are disjoint, then their intersection is phi, which is a member of S. So that's the trivial one. So in case they are disjoint, then intersection is equal to phi, and phi is a member of S. And the second case is if one of them is contained in the other. That case again trivial, because the intersection is the minimal interval, which is minimal among these two intervals. So let's take the first case. If A1, B1 intersection A2, B2 is phi, then trivially, then it's a member of S. And we don't need to prove this case. In case they are disjoint, because we have to show that the intersection should be the member of S. In case they are disjoint, then the intersection is phi, and phi is a member of S. And second case, if they are not disjoint, but one of the semi-closed interval is contained in the other interval. If A1, B1 is contained in A2, B2, or A2, B2 is contained in A1, B1. So that's a similar case. So I discuss only this case. If A1, B1 is subset of A2, B2. So this is this one. This situation is like if we choose, let's take this as a real line, and then A1, B1 and A2, B2, they are the real numbers such that A1, B1 is subset of A2, B2. It's like this. A1, B1 is here. It's semi-closed interval. And then we have A2, B2. But A1, B1 is subset of A2, B2. That means A2, B2 is bigger than A1, B1. So it's like this. It's A2 is somewhere here. And B2 is somewhere here. We show that intersection is again a member of S. Now you can easily check that then this intersection A1, B1 intersection A2, B2, or you can directly see this, it's a subset of that set, therefore intersection must be equal to this one. It's equal to A1, B1 with some member of S. So first case, if they are disjoint, then intersection is a member of S. Second case, if one of the set is, or one of the semi-closed interval is subset of the other, then the intersection is that one which is a member of S. Now third case, if they are not disjoint and one of them is not contained in the other. So that's the third case. That's the most general case. Third case. If A1 intersection A2 B2, A1 B1 intersection A2 B2 is not equal to phi, and neither A1 B1 is substop A2 B2, and neither A1 B1 is substop A2 B2, neither A1 B1 is substop A2 B2, nor A2 B2 is subset of A1 B1. Then situations like this, it's A1, it's B1, and A2 B2. A1 B1 intersection A2 B2 is not equal to phi. That means these two intervals must intersect such that neither A1 B1 is substop A2 B2 nor A2 B2 is substop A1 B1. The situation is like this. A1 B1 must be, say, somewhere here. The A2 B2 must be here. This B2 cannot be less than B1, because in case B2 is less than B1, then A2 B2 is subset of A1, which is not the case. And again, this A2 cannot be less than A1, because if that happens, then A1 B1 must be subset of A2 B2, which is again not the case. So situations like this, in case they are disjoint, in case they are not disjoint, and if they are not, if one of them is not contained in the other, then you can see that this intersection A1 B1 intersection A2 B2 is equal to, what's this, A1 B1. A1 B1 is this set. Its intersection with A2 B2. A1 B1 intersection A2 B2. It's A2 B1. It's again a semi-closed interval. Therefore, it's a member of S. So thus we have discussed all the three cases. So therefore, this S is closed with respect to finite intersection. Now we verify third property. Third property means if I choose any two members of S, then their set difference must be equal to the finite disjoint union of members of S. So let's take a third property. Let's check a third property. Choose any two members of S. Let A1 B1 comma A2 B2 be any two members of S. We show that A1 B1 minus set difference A2 B2 is equal to C1 union C2 union so on up to Cn, where these Ci's, they are the members of S and they are also pairwise disjoint. This is equal to phi for I not equal to G. They are disjoint. That's third property. For any two members of S, we need to show that the set difference is equal to the finite disjoint union of members of S. So let's prove this property. Again, we discuss three cases, as we had discussed in the second one, where we have proved second property. We have discussed these three cases. First case, if they are disjoint. Second case, if one of them is contained in the other. And third case, if they are disjoint in neither, but one of them is not contained in the other. So again, we discuss here three cases. Case number one. If they are disjoint, if A1 comma B1 intersection A2 B2 is equal to 5. So here the situation is like this. A1 B1 and A to B2, they are disjoint. Therefore, A to B2 must be somewhere here or somewhere here, A to B2. Now we show that the difference of these two sets is equal to the finite disjoint union of members of S. So let's find the difference of these two sets. A1 B1 minus A2 B2 is equal to A1 B1. You have to remove A2 B2 from A1 B1. So that's equal to A1 B1 because they are disjoint actually. It's equal to A1 B1. So it's equal to A1 B1. It's equal to A1 B1. And it's clearly a finite disjoint union of members of S because we can insert phi here, or it's one member is enough. So this set difference, it is equal to the finite disjoint union of members of S because they are all members of S. A1 B1 is a member of S, phi is a member of S, phi is, they are all members of S, and they are also pairwise disjoint. So in this case, it's done. This set difference is equal to the finite disjoint union of members of S. Now we discuss second case of it. Second case of property. Third. Case 2. Case 2. Suppose they are not disjoint, but one of them is contained in the other. Suppose A1 B1 intersection A2 B2 is not equal to phi, and one of them is contained in other. See, A1 B1 is subset of A2 B2, or A2 B2 is subset of A1 B1. That's case 2. That's case number 2. Okay. So these situations like this, it's A1 B1 is contained in an A2 B2. A2 B2, or A2 B2 or A2 B2 is contained in A1 B1. So these two cases here. Now we find the set difference. We have to show that set difference is equal to the finite disjoint union of members of S. Let's find that set difference, A2 B2. So suppose A1 B1 is contained in A2 B2. Now what's A1 B1 minus A2 B2? A1 B1 से आपने A2 B2 को remove करना है. A1 B1 from A1 B1. So A2 B2 is a bigger set, A1 B1 is smaller set. So when we remove bigger set from a smaller set, it's equal to phi. And phi is a member of S. So that means this difference is finite disjoint union of members of S. Or let's do this case, A1 B1 minus A2 B2. You have to remove A1 B1 from A2 B2. It's equal to A1 to A2 union B2 to B1. It's equal to A1 to A2 union B2 to B1. They are members of S. So therefore this difference can be written as the finite disjoint union of members of S. Okay. So So that's case 2. So in this case, we have proved that the set difference of two members of S is equal to the finite disjoint union of members of S. Now the last case, that's case 3rd. In that case, again they are not disjoint, but neither this is a subset of that, and nor this one is subset of this set. But they are intersecting with each other. That's case 3rd. Case 3rd. So if A1, B1 intersection A2, B2 is not equal to phi, but neither A1, B1 is subset of A2, B2, nor A2, B2 is subset of, oh sorry, it's neither this is subset of that, nor this is subset of this. Okay. Subset of A1. Okay, sorry. This is case 3rd. In this case, the situation is like this. It's A1, B1, and it intersects with A2, B2 because the intersection is non-empty. They are not disjoint. And at the same time, neither A1, B1 is subset of A2, B2, nor A2, B2 is subset of A1, B1. So therefore, situation must be like this. It's A2 must be somewhere here and B2 must be somewhere here. Or A2 must be somewhere here and B2 must be somewhere here. So let's look at this. We find the set difference A1, B1 minus A2, B2. So here it's like this. It's A2, B2, A1, B1. So let's find this set difference. So we have to remove A2, B2 from A1, B1. A2, B2. हमें A2, B2 को हमें remove करना है A1, B1 से. That's the point here. So how do we remove this? If we remove A2, B2 from A1, B1, so what will be the remaining portion? It will be equal to A1 to A2. It's equal to A1 to A2, and it's a member of S. Therefore, this difference can be written as finite disjoint union of members of F. You can insert phi here. Phi. Okay. So thus, in all these three cases, the set difference of two members of S can be written as a finite